Hello everyone. Today we are going to talk about operating vehicles using search algorithms and equation-based optimization algorithms. So first, some hard facts on self-driving vehicles. Currently, there are some practical issues using self-driving vehicles in real-world situations, such as legislations or security concerns. So it's more practical to use self-driving vehicles in a more contained area. So for example, a theme park. So if you have been to the Universal Studio Tour in LA, basically they move you from point A to point B, and we want to design a shortest path that will take you from a point A to point B, and at the same time we want to avoid hitting the obstacles. The obstacles can be the tree on the road or buildings that you don't want to enter. So we assume that we know the location of the obstacles and they are fixed. So we propose the following three solution strategy to solve this problem. First is A star and its variants. And secondly, we want to use A star based rapid exploring random tree or called RRT algorithm. And lastly, we want to use the equation based optimization strategy. So I don't need to remind you what A star is. Basically, we use the standard A star search as the baseline comparison. We also apply the theta star. Lastly, we use the lazy best first search. The essence of this algorithm is basically to minimize the time that we evaluate the edge weight function, considering that this step is very expensive. So with RNT, the original RNT algorithm basically samples point from the whole diagram so that there's a tree growing from point A to point B. So because we don't have a specific rule of how to sampling the points, so we end up sampling points everywhere and it's not very efficient. In order to improve on that, we use a star-based ART algorithm. Basically, we use heuristic to calculate the cost or the distance of the current point to the target point. So, and among those, we pick up the point with the lowest cost. Um, Lastly, we use the equation-based optimization algorithm. Basically, we assume we know the dynamics of the vehicle operation, and we can manipulate the velocity, magnitude, and directions. As a result, the problem we solve is a nonlinear programming problem, and we solve it with an interior point solver called IPOpt. So due to the restriction of the time, there are just three sample results that I want to show you. So the leftmost diagram is for the standard A star. As you know, it's not very good because the restriction that we put on the A star is that the path has to stick with the grid. Well, the right two diagrams that we calculate using the A star based RNT and optimization based algorithm can obtain similar results. Thank you for watching.